parts with each half core connected in parallel. And how is the machine connected? And the state windings are in Y mode. So the machine looks like this. These are in parallel. So it looks like this. Oops. Yeah, some of these lectures stress the students out. I don't know why. It's just the way it is. Some things will never change. Okay, so that's there. It says the state windings in two parts with each coil, half coil, but that means each coil, connected in parallel. So they're in parallel. And the stator connected in Y. So the whole thing is in Y, but within the phase, each phase is in parallel. So that's it right there. Partial details on the rating plate are as follows. So the nameplate data, this motor is 350 horsepower. Okay, that's the maximum rating. The voltage is 480 volts. And the frequency is 60 hertz. So that means from here to here is 480 volts. That's V line. $480. With the above in the power factor and efficiency respectively, that means the power factor is 0.83. And the, what else? The efficiency is 0.92. And the efficiency, which is 92%, but I can't use percentage in a calculation, so I have to convert it to decimal. Divided by, percentage means out of 100. I divide it by 100 and I get 0.92. And then what do they say to find? The output horsepower, if the current at the time is 195. So they say, okay, if the current flowing right now is 195 amps, then find the output horsepower. So this is 1. Find the output horsepower. This is this one here. Now, this is the horsepower of the machine here that's given. So if you're being asked to find the horsepower, then that tells you that this current here is not equal to the full load current. This is not the full load current, because when the full load current is flowing, the motor should be developing its full rating of 350 horsepower. So this current is not full load, which means this horsepower here that you've been asked to find is not the rated horsepower or the maximum horsepower. So it must be less than 350. That much I know. So I go to the formula for horsepower. Horsepower for a three-phase machine would be √3 times the current, times the voltage, times the power factor, times the efficiency. And all that will be divided by 746. That converts it to watts. That means this numerator is in watts. This denominator, when I divide by 746, I convert it to horsepower. Okay. So if I do this, then this therefore is equal to P in watts. That right there. But since I wanted horsepower, then I have to do this. Nope. Then I have to divide this by 746. And now my answer is in horsepower. So this is blah, 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 so many horsepowers. So I put the numbers in. √3 times 195 times 480 times 0.83 times 0.92, all divided by 746. So what is the output horsepower? So somebody do that on calculator, please. Anybody done? Who's calculating? Bruce, you calculating? Where's Bruce?
Calculator now.
Okay, let me know what your answer you got.
Okay, I got 165.94.
Oops, hold on. 165.94 exactly, only two decimal places.
No, I rounded.
We rounded to 3 or 4.
Okay, so that's 0.9448.
4, 4. Okay, so that's the answer for number. So this is number 1. Okay, any questions there? All right, no questions. Super. Okay, so let's go to 2. 2 says to find the current. So to find the current, we're transposing this formula here. Transpose that to make I the subject. So I is equal to carry the 746 over with this is horsepower over here. So you have the HP, and this is the rated horsepower, because notice this says the full load. So this is HP rated. It's the rated horsepower. Oh, wait. This is the rated horsepower times 746 over root 3 times the voltage times the power factor times the efficiency. Okay, so this is going to be, so I is going to be, this is the full load current. Let me write that in there. I full load current equals, and this is going to be 350? 350 times 746 divided by root 3 times 480 times 0.83 times 0.92. Okay, so work that out. Hey, somebody's calculating Bruce. Let's see. Bruce got to go do something. Someone else calculate. Let's see. Kristen, where's your calculator? Oh, Kristen.
I got it right now.
Go ahead. Get cracking.
Hey, Mr. Umbresta, this answer would be a milliamp.
No, sir. Mm-mm. That gotta
We
be a
got
plenty
it.
of. You use 92 it.
Let me
Use
let
90.
me double check.
Don't use 92. Use 0.92. And make sure you work out the square root depending on how your calculator work. You have to know how to use the square root because it may end up taking the square root of that whole number rather than just the 3. So what's going on? Your calculator freaking out or something?
I got 2 errors. Hold on. I just trying to make sure I put it in right.
Do the top and then do the bottom, then divide it.
Yeah, I did. I doing the bottom now.
The reason I asked, I got like 411.281.
That ain't no milliamps.
That'd be in amps. I just saying that sound like a big value for amps.
Well, this current right here is 195.
All right, yeah, all right. All right,
And that's not the full load current.
Yeah, I go for 11.
That's what he said. 411 point what?
2.8.
28 what? How many more decimal places? Give me 2 more.
1.4.
14?
Yeah.
14 amps. You know, when you build an electrical supply like a service, you could build a 2000 amp service. Like the breaker box, you could build a breaker box for a 2000 amp service. That's way more than 400. Okay, that is 2. So this is 2. Okay, any questions there so far? 0 zilch. Whoa. Okay, so let's go and find number 3, the input power. Okay, so what is the efficiency equal to? Okay, when you put power into something, what do you want to do? What you want to happen? And do what? And do what you wanted to do that. How good do you want the load to do that? Yeah, but okay. If you put okay, let's say you hire somebody and you pay them $100 a week. What would you want to get out of them? What do you want to get out of that person you hire and you pay them $100
worth of work.
You want to get $100 worth of work. If you pay them $100 and you get $100 worth of work, then how efficient is that? How efficient is that person?
100%.
Okay. What if you hire a person, you pay them $100, and you get a little less than $100 worth of work out of them? What would you say? What would you say? How efficient would you say they are?
Say it again. Sorry, I couldn't hear you. Is
You
if it's a
hire a
little less?
person and you pay them
Little less than
$100 a week,
100%?
right? And what they give you is a
Little
little
less
less
than
than 100%. A little less than 100%. How efficient would you say they are?
Just about perfect. Yeah. Slightly.
Say it as a number.
Oh, 99.99.
Okay, 99.99%. So in order for you to get that number, what comparison did you make? In order for you to get that 99%, what two values did you compare?
The 100 and the 99. 100 minus 99.
No, not minus the 99, because you said if you say 100 minus 99, you get 0.001. So what did you compare and how did you do it? Huh?
All right. I compared the result I put in compared to the result he gave me out.
You compared what you put in to what you got out.
Compared to what I got out. Yeah.
So if you compare what you put in to what you get out,
I divide.
so what number you divide the 100 by the 99?
I mean, if you asked how we get percent, I would have said it would have been 100 minus 99.9 divided by 100.
No. You're not subtracting. You're comparing two things. 100 minus 99 is point something divided by 100 will give you one point something 1%. That's not what you did.
Yeah.
So you said just now that you compared what they put in and you compared that with what they got out. Is that what you said or what you mean?
Yeah.
Okay. So which number are you putting in the numerator?
The output.
So if you put the output in the numerator, then you can't say that you're comparing what you got out to what you put in to what you got out. If you said if you said I'm making a comparison of what I put in to what I put out, that's what you're saying there. But now you're telling me you put output in the numerator. So that means you are you now saying that you're comparing what you got out compared to what you put in? Which is it? Huh?
I get with the first thing I say. I comparing what I put in to what I get out.
Okay. So you said you gave them 100.
And I get 99.9% out. I mean 99.9 out.
Okay, so divide that for me. Let him divide that. What you get when you divide this?
One. Basically one.
Basically, 1 point what?
Basically one. 1.0001.
Okay.
1
So,
point.
so 1.
Yeah.
Okay, convert this to 100. So that means the person did less work than what you paid for, but they still 100% efficient. You see that? Is that possible? Not possible. So you're doing this one. You keep comparing the output with the input. can the output ever be bigger than the input? Okay.
No, it can't be. The output can't ever be bigger than the input. If it's going through something, no. That would be
Okay.
some kind of loss can happen.
So you're saying the output is equal to the input minus the loss. Is that what you're saying?
Yeah.
So if I make P in the subject, you're saying that P in is equal to P out, and I carry the loss over, it becomes plus P loss. Saying basically what you get out compared to this is what you put in.
Yeah.
You agree with that?
I feel like it made sense. Yeah.
It's sensible. Your input is whatever you get out compared to your loss. Because if you're here P in, you have to leave from here to go to P out. But in between here, something happens. And the thing that happens in between here is the loss. If you take a gallon of water, if you put 1 gallon of water, okay, let's go to the gas station and you order a gallon of gas and you put that gallon of gas in your tank. Would that be a gallon of gas? Yes or no? When you buy a gallon of gas, do you get a gallon of gas in your car?
I can't answer that for legal reasons. Let someone else answer that.
Okay. If you order a gallon of gas, when the gas goes in your tank, does a gallon of gas go in your tank? Well, let's say they're doing it legitimately. Let's say they're honest and they're giving you legitimately 1 gallon. How much gas would be in your tank? Because you heard what? No, we're not talking about starting the engine. We're just talking about what they put in the tank. We're not starting the engine. They're not responsible for that. It can't be a gallon because some of the gas evaporates while it's going in there. You have evaporation. Okay, and then so you're gonna have some drip out. What about the lining of the hose? Does some gas doesn't so the once the gas hits the hose, some of the gas is on the lining of the hose. All the gas doesn't come off. So you're gonna have some gas on the lining of the hose. Okay, it's just like water. If you have a gallon of water in a bottle, and if you have 1 bottle with a gallon of water, and you put in another gallon bottle, does the whole gallon of water go in the next bottle? It can't go because you're gonna have water still lining the first gallon that couldn't come out. That's why you're always shaking it like that, trying to get every drip. You're still gonna end up with some water on the lining of the inside of the bottle. And you may also have some evaporation take place depending on the time of the day. You see, so so for all those kinds of reasons, so all that that's lost. That means your efficiency in transferring a liquid from one container to the next is not 100%. It might be 99.999, but 99%. There's going to be some losses. The same thing happens. But when you have efficiency, efficiency can't go over 1. It cannot be bigger than 1. In order for you to have an efficiency of 100%, it means you got out exactly what you put in. But you could never get out exactly what you put in because it means you have no loss. And that means the system is perfect. That will never happen. So your out is always going to be smaller than your in, which your efficiency can now never be 90, can never be 100%. It's going to be like 99 or 98 or 92, like in this example. It's just like when a lady, a girl comes to you and says, I love you 110%. You like, you shouldn't be getting excited about that because she lying, you know? So, she can't love you more than what she has, the love that she has to give. How can I love you? How can she love me 110% when she only have a love of 100%? Where's the 10% coming from? You see? No, Jesus. So you get my glass. What overthinking that? She ain't love you. She's saying more. She's saying more love than what she have to give.
She said she borrowed an extra 10% from us. Stop.
Yeah, exactly. So efficiency is always going to be a comparison of P out compared to P in. And what does this question ask you to find? It asks you to find the power in. So if the output power of this machine is 350 horsepower, what does that tell you about the input? Huh? If the machine is, it's more than 350. Because for you, if your output is 350, it means the machine has to do more than 350 for you to get 350. So whatever this answers you're looking for in number 3, you know it's going to be bigger than 350. So if I transpose this to make P in the subject, this is going to be P out over P in. And what is P out? 350. And what is not P in? Why are you making, let me do that. It's efficiency, sorry. It's efficiency. Efficiency will go on the bottom. And this will be 0.92. How much is that? $350 divided by 0.92. Bruce, you still entertaining? Hey, Bruce?
No, I just got bugged.
Oh, 350 by 0.92 somebody.
That's
380.
380. Yeah,
Yeah.
0.43.
380 point what?
43 48.
4348 horsepower. Because we gave this, because this 350 is an horsepower. But look at the question. The question says what? Give your answer in kilowatts. So first we have to convert this to watts. Let's convert it to watts first. And we know that 746 watts equals 1 horsepower. Since this is in horsepower, I want horsepower on the bottom. So this is an identity. I want to divide both sides by 1 horsepower. So this then becomes 746 watts per horsepower would be equal to 1. So that's the multiplicative identity. So I can multiply by that. So then it means P in and watts would be 380. Notice the 380 is bigger than the 350, which is what we said. 0.4348 times 746. The horsepower cancel, leaving the answer in watts. So P in is equal to how much? 380 times 746. How much is that?
Okay. So it's 283804.3608.
And this would be in watts. And then to get it to kilowatts, you need to divide by 1,000. So Pn equals 283804.3608 divided by 1,000, which is going to be 283.804 kilowatts. Yep. So that's how you do 3. All right. Any questions so far there? Okay. If no questions there, okay, let me show you a little something. Okay, let me show you a little something. If I say efficiency, no, if I say Pn, if I say Pn equals P out over efficiency, then that equals P out. Well, we know what P out is. That's what we did when we first started. That is root 3 times I times V times the power factor times the efficiency. Right? Divided by the efficiency. So what does that mean? That means efficiency can cancel efficiency. And that can leave us with Pn equals root 3 times IV times power factor. And that would give us the power in. And that would give us power in watts. So let's see if that works. So let's go root 3. And this is the full rating. So that means the current we're using would be the 411. So it's going to be 411.2814 times the voltage, which is 480, times the power factor, which is 0.83. Okay, somebody calculate that.
Yeah, it's basically the same. It's the same 283804, but then the decimals are different.
804 point
336 this time.
336 watts. Okay, why is it different? What happened right here? What happened there, and also what happened here? See, in both of those cases, we rounded off the. Wait, hold on. What is this? Pn Why did I put P and it's equal to this? Oh yeah, it's P and that's the route. That's right. Not this. Yeah, we rounded off this number here. You see, when I use this number over here, I use this number here that I rounded off. And then we rounded this number off too. So this goes on a bit further. And so when we multiplied this number would have been a little different if we didn't round that off at that point. And then when we ran over here, we used the 2814, which was not the entire amount of decimal places. So if you were to be more accurate with it, and then it depends on whether you use 1.732 here or root 3, and what did you use when you did it over here. So it depends on things like that. But it's the same answer. But let me ask you a question. What is the power triangle? What is the power triangle? It's the power triangle, right? This angle here is theta. This is P, which is in watts. This is S, which is in voltamps. And this is Q, which is in vars, volt-amp reactance. Okay? So why triangle, the power triangle here? Okay, well, let's see. Let's make a little space here. I'm going to put in the power triangle here, but let's see. How do I, if this here, okay, S, this is voltamps. S is the apparent power. This is the apparent power. S is equal to, if it's measured in voltage times amps, that means the formula for S must be IV. Because A is where you get, that's I, and V is volts is voltage. So this is the apparent power here. This is the apparent power. This is the apparent power. This down here is the true power. This is the true power. That looks like true. I don't know. This is the true power. And this over here is the reactive power. That's the reactive power. Okay? How do I solve for P? How do I solve for P? P is the adjacent.
That'd be what? S cosine theta?
That'll be S cosine theta. Oops. That'll be S cosine theta. And what is S equal to?
I times V.
So therefore, this is IV cosine theta. And what is cosine theta equal to? What is cosine theta equal to?
What is that? P divided by IV? I mean, the power factor.
Cosine theta is the power factor. Yeah, that's the power factor. Theta is the power factor angle. And the cosine of that angle is the power factor. That's how you got this 0.83. That's where it comes from. The cosine of whatever angle is between the true power and the apparent power will give you this degree right here. And when you take the cosine of that degree, that's how you got the 0.92. See? This power here, this P here represents resistance. Any power that is burnt in the circuit in resistance, only power burnt in resistance can give you watts. Only power that uses reactance, which is X, XL or XC. In this case, the motor, we're talking about XL. only power used up by, well, not used, well, you could say used up by the reactants can give you reactive power. And this apparent power is the power that's used up by the what? By the Z, that's the impedance. When you have a circuit, a circuit has resistance in it. The power burnt in the resistance is the true power. That's measured in the circuit. You're gonna have inductance in the circuit, mostly inductance. Sometimes some capacitance, sometimes very little capacitance. So the reactive component in many circuits would be the inductance. The power that's used by the inductance is the reactive power. So you have two sets of power being in the circuit. A circuit, the components in the circuit has to either be resistive, capacitive, or inductive. The resistive is the true, that's where the true power comes from, and the inductive and the capacitive, that's the reactive power. Those two powers together gives you the total power in the circuit, because resistance and reactance gives you impedance. And impedance is the total opposition in the circuit. Resistance is the opposition to DC current. Reactance is the opposition to AC. And when you combine the DC component and the AC component, you get the impedance. So the overall opposition in the circuit is the impedance. That's the combination of the resistance and the reactance. But they're quadrature components, or they are complex components. So you have to add them. You can add them algebraically. They're in different planes, and so on. So if you look at this, if I go in and if I knew what the resistance is in this circuit, and I draw what we call an impedance triangle, where this is R, and where this right here is X, and then I will find Z here. This angle right here, that will be the same power factor angle. This angle and this angle in the power triangle and angle in the impedance triangle, this is the impedance triangle. They're the same angle. And you can do this over and over and over again, because you can do the same thing for the current. Because if I find IR and I combine it with IX, I'm gonna get IZ. And the angle between them will be theta, same theta. And if I take VR and compare it with Vx, and I find VZ, this angle will still be the same power factor angle. So the power factor angle is the angle in the power triangle, in the impedance triangle, in the current triangle, and in the voltage triangle for a given circuit. But anyways, so back to here. So this is P is equal to IV cosine theta. So then you're going to say P is equal to, and it's a three-phase circuit, so you need to put √3 in front. And then you're going to put IV, but instead of cosine theta, you notice the power factor. So you're going to put PF instead. Okay? And so there you have the formula. That's right there. That's PN. And so once you want the power in watts, because remember this says to find the power in kilowatts, that's watts. Okay, so if you take the formula, the general formula for power, √3 equals IV times power factor times efficiency, you drop the efficiency and you'll get your input power in watts. So you could, huh? That's PN, right? This is PN. Yeah, this is PN right here. So you could find PN like this, or you could find PN like this. Either one. You could do this one or that one. Divide the power out by efficiency, or do this right here and get the same answer. Just like we got this answer here. Oops. Just like we got this answer here. And you divide that by 1,000, you get 283.804. Okay, questions there? You got that? Is that cool? Yeah? All right. So I'm going to do one more, and then I can let you play with these other two. homework. Let's go to this number 4. Let's do this one right here. So I'm gonna make some space here. You don't need all of this anymore. Just get rid of all of that. Okay, so let's see what we got. It says the current carried by 1/2 coil, that means one of the windings of the stated windings, using the information from 2. 2 is when we found the full load current, that's the 411. So basically what this is saying is if this current coming into here is 411.2814 amps, then what is the current that's going through here? So 1.5 coils. Okay, this is the line current. This is equal to I line. But where does the line current go? This current here, where does it go? It goes straight down into here, which is the phase current. So what does that mean? That means I line and Y is also equal to I phase, which is also equal to 411.2814, right? 4 amps. That's the phase current. And now, once you go across the phase, everything is vectorial or phasoral. But within the phase, everything is algebraic. So once you come here, this is a general parallel circuit. The current will split up into 2 parts. It'll split up into 2 parts. One will go down that leg, and one will go down this leg. So that means I coil is going to be equal to I phase over 2, which is going to be 411.2814 over 2. Okay, somebody divide that. So that means I coil 2 into 4 goes twice. And then this is 0. And 2 into 11 goes
205.6407
amps. Yep. And so that's how you do that. All right, so what are your questions? No questions. All right, so play around with this number 5. Number 4, number 6 you should be able to do. And all number 6 is saying is make each one of these here, get a different color. Make each one of these coil here have a resistance of 2.5 ohms. And therefore, if I look into here, what is the resistance I should see? And you do that with all the coils healthy, 1 coil shorted, 1 coil open. So you ought to know to do it by then. If not, I will show you that on Thursday. And then this one here, I think I went over this, but I'll do it again. The maximum of voltage occurs here in Y series. And the minimum occurs in delta parallel. Delta parallel. Yeah. So we'll have to convert to delta parallel and then work it out. Work out the supply voltage and current, and then convert to Y series and work out the supply voltage and current. So that I'll do that on Tuesday. Sure, I'll do that there. So we'll finish. Try part 6 for just play around with it, see if you get it. For all the coils healthy, and then 1 coil shorted, and then 1 coil open. And then we'll do 5 and 6 on Thursday. All right. All right. Any questions? Anybody? Nope. All right. So
Okay.
see you then. Yeah. All right.
All right.
See you later. Thanks.
Yeah. All right. Later.
Yes. Mm-hmm. Are you attending what? Yeah. Will it affect you? Affect you? How? What do you mean affect you? You mean like you think if you do still do okay in the classes and stuff? Well, correct classes will always be in the morning, like around somewhere between 10 and 12 or something like that. So I mean, you'd be able to go to the classes if you have your job in the night. Um, and the question would be whether you keep up with the work. Yeah, the question would be whether you put the time in it, like whether you stay awake in the class when class is going on, and two, whether you put in the work. You know, I mean, because he doesn't give too much leeway. He's a little better now, but he still doesn't give too much leeway. Yeah. So yeah, so once you focus on the work and put the work in, if you put the time in, you'll get it. Huh? I don't think you'll have a problem. You know, the main thing is the only place you may have trouble is with cartwright internal. Yeah, because Turner could be a little bit rigid, and then cartwright is always rigid. Right. Mm-hmm. You finish your math? You already do one. Oh, so yeah, so you wouldn't have any problem. Some math lectures are a little finicky too, but if you're finishing up your math, then you should only have general education classes and your major classes and stuff like that to do. And so yeah, you could tug that out, but you have to put the work in, and just stay alert and put the work in and find some time to sleep in between. 271, I think. Yeah, no, I think she may think you're in engineering, the associate's degree. Yeah, that's differential equations, but that's not on the. Hold on, let me double check. I don't remember that. I don't remember that being on the lexical program. Hold on, I can check right now. I remember. I don't remember 274. No, it's the electrical. Okay, let's see what it is. Let me see. Two. There are 167, 168, 171, 271. No, only 271. She's thinking about the engineering program. Yeah. All right. Cool. Yeah, no problem. See you later. All right. Goodbye.